Hello everyone, my name is Brooke and today I will be presenting on the Delian problem, also known as doubling the cube, and I will explain where both of those names came from in just a little bit. So to start us off, I'm going to talk about the Greek problems of antiquity. So over time, there have been three claimed problems of antiquity from the Greeks, meaning that the solution was sought after using only an unmarked straight edge and a compass. Up to today, we know that those three problems are squaring the circle, doubling the cube, and the angle trisection problem. So starting off with a quick story, around 430 BC, historically a horrible plague hit Greece. Many people died from this plague. The citizens of Delos, which is an island off of Greece, began to search for a cure to this plague. Many times in ancient Greece, they would consult the oracle at Delphi for knowledge or wisdom. And so that's what the citizens of Delos did. They consulted the oracle, asking the god what they could do to rid Greece of this plague. The oracle responded saying that the Delians must double the volume of their altar block to the gods. And this altar block is claimed to be a generic cube. So this is where the problem comes in place. That's why it's called the Delian problem, because it originated from the citizens of Delos. So let's jump into the actual problem. So initially, if we think about a generic cube, imagine that it has side length x. We have the volume of that cube equaling x cubed. Now let's name the side length of the double cube as side length a. What we find is in order for this problem to be true, a cubed must equal 2 times x cubed because we want to double the volume. So to simplify this, we take the cube root and we get side length a equals the cube root of 2 times x. That's where we run into a problem. So the thing is, we know the cube root of 2 is an irrational number. Therefore, we ask the question, how can we increase a side length by an irrational number length? Well, in short, we can't. Specifically, the cube root of 2 comes out to be 1.25992104,989, so on and so forth, ... As we can see, this is a very long, very irrational number, which is non-constructible. As far as constructing this cube, the Delians were out of luck, as this is an impossible construction. So the Delian problem basically said, can you double the volume of a cube with only using a straight edge or a compass? That's also why it's called doubling the cube, because that's what we're being asked to do. So over time, many have tried to solve this problem in other ways besides the original straight edge and compass way. Obviously, we can conclude that this problem is impossible in the way of a physical construction because of what we just talked about. Over time, many mathematicians have attempted to solve this problem, however, each have failed. Across my research, I came across multiple different mathematical attempts to this problem. Archytas, he used 3D solids. He used a cone, a torus, and a cylinder, and attempted to find their intersection point and claimed that the intersection point would be that new side length. Eudoxus was a student of Archytas, and he kind of used the 3D solids method where they intersected but projected it onto an XY plane, so made it into a 2D. Menaechmus, he used cones. All these attempts were very complex and very in-depth, but ultimately there was no derived solution from any, and there was more attempts. Plato attempted it, there were others, but obviously it all boils down to the fact that the cube root of 2 is an irrational number, therefore it cannot be constructed. So that brings us to years and years later, 1837, a man named Pierre Wantzel completed a proof that proved that the cube root of 2 was not constructible. So after all this time of this problem being attempted and being failed, but never formally being declared impossible, this proof formally proved that this problem is impossible. I looked over the proof and it is very complex. It's split up kind of into 4 parts. The first part, it initially tries to change it from more a geometric approach to an algebraic approach, and then from there it tries to break it down, bringing it to the final solution that it is inconstructible. So this ties back to the fact that this is a problem of antiquity. The basis of Wenzel's proof, aside all of the algebra and everything, that the problems of antiquity were based solely off of are they constructible with a straight edge and a compass. And obviously through the proof and through what we know now that this is impossible. So cultural context, one generic thing was geometry was highly being developed in ancient Greece around this time. We know at the time around the same time that this problem was posed, Hippocrates of Chios began to write some of the first elements that began to compile to form what we know now as the elements of geometry. So yeah, originally this problem was approached geometrically, but what we saw on the last slide is that Wenzel took those geometric approaches and tried to change it into more an algebraic approach and then got to his proof, but originally it was approached through geometry because that was the key form of mathematics in this time in ancient Greece. This problem is one of the 3 Greek problems of antiquity, as we've said multiple times. So that's one of the lasting impacts, is it's still a memorable problem in the development of geometry is what we know it today. This quote from one source I found claims that there are 3 classical problems in Greek mathematics which were extremely important in the development of geometry. These problems were those of squaring the circle, doubling the cube, and trisecting an angle. It is fair to say that although the problem of squaring the circle was to become the most famous in more modern times, certainly among amateur mathematicians, the problem of doubling the cube was certainly more famous in the time of the ancient Greeks. So doubling the cube was a strong geometric problem in the time, and it was very famous during the time of the ancient Greeks up until for a long time, and then it was still posed up until when Wenzel proved it being impossible in 1837. That concludes my presentation, and thank you.